10.7, everybody, let's get after it. Here's the question for today. How long is the hypotenuse of an isosceles right triangle as compared to one of its legs? Now, let's consider this fact before we even begin to answer that question. If the triangle is a right triangle and an isosceles right triangle, meaning both of the legs are congruent, then both of the acute angles must be congruent also. They must both be 45 degrees each. And so we have two names in the math business for this kind of a triangle. We sometimes refer to it as an isosceles right triangle, and sometimes we refer to it by the title of this lesson, a 45-45-90 right triangle, which may remind you of the name of the other special type of right triangle we learned about in the very last lesson, a 30-60-90 right triangle. Okay? So that's the type of triangle that we're talking about. And we're going to answer this question the way we did in the previous lesson, which is to use the Pythagorean theorem and do some algebra. If both of the legs are the same length, because it's isosceles, then we can and should call them by the same expression, x. So using the Pythagorean theorem then, x squared plus x squared is equal to the hypotenuse, which I'm calling c squared. And I just turned that equation around, but it's the same thing. Well, combining the two x squareds, and that first x squared doesn't look so much like an x squared as it looks like an x times 2. All right, just ignore that. That should be an x squared. All right, so adding the first x squared to the second x squared, we get 2x squareds. And now solving for c, by taking the square root of both sides, we get c is equal to the square root of 2x squared. But now I'm going to do something very much like what I did in the last lesson, which is to say that the square root of 2x squared is the square root of 2 times x squared, which can then be split up into the product of two separate square root terms. And then what is the square root of x squared? If you square something and then take the square root, you're right back to where you started with x. So square root of 2 times x. And again, we prefer to write this expression with the x in front of the square root of 2, because if you're careless and you write it like that, then people are wondering, wait a minute, is that x supposed to be under the square root or not? And we eliminate that ambiguity by putting the x in front. And what this result tells us is that whatever the leg length is, that's what that x means. It stands for any possible leg length. Whole number, fraction, decimal, could be anything. If you multiply that leg length by the square root of 2, you have exactly the hypotenuse length for any, now this would be for any isosceles right triangle, any 45, 45, 90 right triangle. So let me give you then one specific example with actual numbers in it instead of all of these variables. Okay, let's imagine an isosceles right triangle where both of the legs are each 1. Okay, so then what would the hypotenuse be? Well, it would be that leg length, 1, times the square root of 2. Now, I could write 1 radical 2, but we don't do that in high school. Come on, please. You don't write 1x anymore. It's not wrong. We just don't do that. You don't need the 1 coefficient in front of something. So just square root of 2. Okay? And let me get rid of this arrow here because it looks like that square root of 2 is kind of pointing towards that x. So here's one particular example of a 45, 45, 90 right triangle. And I remind you, as I did in the previous lesson, that all 45, 45, 90 right triangles would all be similar to each other because they all have 3 congruent angles. And if you even have just 2 pairs of congruent angles, that's enough to know that, well, then the third pair would have to be congruent, and therefore that the triangles would be similar to each other. And again, in today's problems, the new problems for today, we're going to use the fact of similarity to find missing side lengths. Okay, so here are, for example, problems. All of these 4 problems on this page are these new special types of right triangles. You can see in number 1, I have marked both of the legs of the triangle as congruent to each other. Therefore, it's an isosceles right triangle. In number 2, I gave a right angle and I marked one of the angles as 45 degrees. Now, I don't have to mark the other one as 45 degrees. If I've given you a right angle and a 45-degree angle, do the arithmetic. The last angle would have to be 45 degrees. And really, I'm not expecting you to do the arithmetic. If you see a 90 and a 45, just know the other angle has to be 45 also. And likewise with the 2 problems at the bottom. On number 3, again, is marked isosceles right triangle. Number 4 has a right angle and a 45 degree in it. 45 degree angle, by the way, that does say 45 degrees. Don't misread that as 95 degrees. That would not be possible. If we already had a 90 degree angle, you couldn't possibly then squeeze a 95 degree angle into the triangle. But I'm sorry for my sloppy writing. Well, let's find out the lengths of A, B, C, and D in these triangles. And again, I'm going to use similarity as my approach to solving these problems. So if I can get my stylus to turn back on, there we go. I'm going to draw another isosceles right triangle next to this one, and I'm going to mark it 1, 1, and radical 2. That's my special case, 45, 45, 90, that I'm going to use every single time to solve for a missing side in some triangle that's been given to me. The A corresponds to the square root 2. The 6 corresponds to the 1. And I'm going to set up a proportion, which is an equation with 2 fractions in it. A over the square root of, are you kidding me? Come on, stylus. There we go. A over the square root of 2 is equal to 6 over 1. Solving for A could hardly be any easier. Multiply both sides by radical 2. Cancels out the division there. And A is equal to 6 radical 2. Please do not write 6 radical 2 over 1. Okay, we don't need the over 1. That's not simplified if you put over 1. Okay, so there's the length of A. And in this triangle here, again, I'll set up my own 45, 45, 90 right next to it. Mark these as 1, 1, and radical 2. Here's B. That corresponds to this 1. 10 radical 2 corresponds to this radical 2. Setting up my equation, B over 1 equals 10 radical 2 over radical 2. Now look, is there any real algebra necessary to solve this problem? Not really. I mean, B over 1 is B. When I set up the equation, it is just by setting it up, it's already solved for B. Except we really should simplify the right-hand side. Okay, 10 times the square root of 2 divided by the square root of 2, those square root of 2's will cancel each other out, and we're left with 10. Okay, now, some of you, if you're really sharp and you're really quick, you may be thinking to yourselves right now, pay attention to me, you may be thinking to yourselves right now, Mr. Nortillo, you made these problems so difficult, and they were actually so easy. You did not have to go through all of that work to solve those problems. I could tell just by looking at this first triangle here and comparing it to sort of the template triangle or the pattern, that A was going to be 6 times the radical 2. I didn't have to go through all this equation stuff. You didn't have to go through all that. Nortillo, why are you making these problems hard when they're easy? I get it. I get what you're saying. And truth be told, if I were solving these problems, I would have recognized the pattern and I would have been able to come up the answers without going through all this work. And maybe, just maybe, you would too. But I've got a warning for you. Okay? Let's take a look at numbers 3 and 4. Okay? If you're not careful, you would look at number 3 and you'd go, oh, that's an isosceles right triangle because I see the congruent leg marks there. Oh, and the one side's been marked 8. That means I remember the 45, 45, 90 pattern. There's 1, 1, and the square root of 2. So whatever one of the sides is, the other side is times the square root of 2. And you might write down 8 radical 2 for C. Circle it and be on your way and be perfectly happy with that answer, except it's completely wrong. Okay? I mean, let's think about why it has to be wrong from one direction, and then let's find out what the right answer is from a different direction. The square root of 2, approximately as a decimal, do you have any idea what that is? I'll tell you. It's about 1.4. So if you multiply 8 times 1.4, you get approximately 11.2. So what you have written here, if you write 8 square root of 2, is that the length of this leg is 11.2. Now compare that to the hypotenuse, which is 8. If the hypotenuse is 8, can one of the legs be 11.2? No, it can't. The hypotenuse is always the longest side of the triangle. So if you're not careful, if you think you can scoot right to the correct answer to problems like these without going through the similar triangle, setting up the equation approach, my concern is half the time you're going to get the wrong answer. You're going to get it quickly, but you're going to get it wrong. Okay? So how do we do this problem? Well, the way we did the last two problems. Set up another isosceles triangle right next to it. 1, 1, and the square root of 2. That's where those numbers belong. And again, during the quiz, you should have this triangle right here, this specific one with the 1 and the 1 and the square root of 2. Okay, you should have that out, be able to refer to it while you're taking the quiz. I mean, if we were in the classroom, I wouldn't let you do that, but we're not, and I can't stop you. So you should have it out so that you don't make any careless mistakes. I mean, there's no excuse for not having this triangle out and not setting up the equation properly. Now, this C corresponds to the 1, and this 8 corresponds to the radical 2, and so our equation looks like this. C over 1 is equal to 8 over radical 2. Now, again, there is no algebra necessary to solve for C. This equation is already solved for C because C divided by 1 is C. Right? And we see that the value of C is not 8 times the square root of 2, which I had written up there a minute ago. It is 8 divided by the square root of 2. And again, square root of 2 is about 1.4, and 8 divided by 1.4 is about, I don't know, 5.6, something like that, which makes a lot more sense. But this is not a simplified value. So you could circle this and you would have the exact value and it would be correct, but it wouldn't be a simplified value, right? And I'm going to continue to ask for simplified values all the time, unless I explicitly give you permission in the problem to give me, let's say, an approximate decimal answer. You should continue practicing getting simplified exact values. If I ask for that on the quiz and that's not what you give me, you're going to lose credit for sure. So let's remember how to simplify 8 divided by the square root of 2. We got to multiply it by the square root of 2 over the square root of 2. And then multiplying fractions straight across, we get 8 times the square root of 2 over, what's the square root of 2 times the square root of 2? It's the whole number 2. Don't circle that answer because it's still not completely simplified because 8 divided by 2 is 4, right? That can be reduced to a 4. And there is the exact answer, simplified. Okay, let's do one more example like this. Again, if you think you've got the pattern in your head and you know exactly how to jump to the correct answer without doing any work at all, what you would probably do is you would say, oh, well, D's got to be 7 because in these 45, 45, 90 right triangles, there's always like 2 of the sides are whole numbers and then the other one is that whole number times the square root of 2. So if I got a 7 radical 2 here, that's got to be a 7. But again, let's see why that can't possibly be right. 7 times the square root of 2 is about 9.8. If you write that the hypotenuse of this triangle is 7, which is less than 9.8, that makes no sense at all. Okay. So what should D be? Well, I'll tell you what else it's not. It's not 7 divided by the square root of 2 either. Okay. And if you're wondering, well, what is it? Well, don't be in such a hurry. Let's set up the equation. Let's draw our pattern triangle, our template triangle, 1, 1, square root of 2. Let's, identify the corresponding sides, and then let's write an equation and solve it. Okay? There's your correspondences. So what's the equation? D over square root of 2 equals 7 square root of 2 over 1. So this does technically require some algebra to solve it, multiplying both sides by the square root of 2. Cancels out the division by the square root of 2, and we are left with D equals 7 times the square root of 2 times the square root of 2 all over 1. Well, again, we don't need the all over 1 part, but we do need to simplify this. Square root of 2 times the square root of 2 is 2. And so we have 7 times 2, which simplifies even further to 14. Okay? Don't be in too much of a hurry to do these problems. People who are in a hurry always make more mistakes. Okay? Now, let's scroll down. I got 3 more problems and we're done with this lesson. Okay? Number 5 and number 6. Take a look at number 6 before we work on either one of these problems. You see anything different about that triangle? It's not a 45, 45, 90. Okay? In tonight's homework, not every triangle is a 45, 45, 90. Okay? Triangle in number 6 is a 30, 60, 90. Please, please, in the homework, pay attention to what kind of a special triangle you're dealing with, because there's a different pattern for 30, 60, 90s than there is for 45, 45, 90s. And we learned that pattern in the previous lesson. And if you need to refer to the previous lesson and look it up to be reminded of what it is, do it. I mean, I'm going to remind you right here, right now. Okay. You also might be looking at these 2 pictures and saying, wait a minute, Mr. Nortillo, you've got those pictures wrong. Are you thinking that? Are you looking at this number 5, which is an isosceles right triangle, and I've written a 5 radical 3 for the leg, and you're going, that's wrong, Mr. Nortillo. There's no radical 3s in an isosceles right triangle. I mean, every single time you wrote the pattern triangle, Mr. Nortillo, here it is, 1, 1, square root of 2, 1, 1, square root of 2. It's a square root of 2. Didn't you mean to write a square root of 2? No, I didn't. Okay. The leg of an isosceles right triangle can be anything at all. It does not have to be a whole number, could be a fraction, could be a decimal, could have a radical 3 in it, could have a radical 6 in it, could have anything in it. Okay? I want it to be 5 radical 3. It can be 5 radical 3. And then you might be scratching your head again and think, well, how on earth are we going? How can we figure out what the E is then? And if you're scratching your head thinking, well, how on earth can we find the E? You have not been paying attention to what I've already been saying. Set up another 45, 45, 90, put in the pattern, set up the equation, and solve for the variable. This is how you do it every time. It always works if you do this. I just know that some students don't want to go through the work. They don't want to put in the work. They don't want to put in the time. They want to do things too quickly. They want it to be easier. Well, sometimes it's just not. Okay? Since this is an isosceles right triangle, it is similar to this isosceles right triangle. The E corresponds to the radical 2. 5 radical 3 corresponds to the 1. Let's set up the equation. E over the square root of 2 equals 5 radical 3 over 1. Solving this equation for E requires us to multiply both sides by the square root of 2. We don't need the over 1 in our answer, but what is the simplified answer? What is the square root of 3 times the square root of 2? It's the square root of 6. And so our final simplified answer is 5 square root of 6. Does that surprise you? Well, be surprised. Okay? So none of the sides in this triangle are whole numbers. I mean, this side right here, it's marked congruent to that one. So we don't have to figure that side out at all. We know it's 5 radical 3, same as the other leg. And then the E turned out to be 5 radical 6. So none of these sides have whole numbers, and none of them have square root of 2's in them either. Okay? I'm trying to make sure that you hear me on this. I'm raising my voice, okay, so that you hear me that this pattern does not mean that the two legs of a right triangle or that any two sides of a 45, 45, 90 right triangle are going to be whole numbers, and that the other side, the third side, or the hypotenuse, is going to have a radical 2 in it. That's not what the pattern tells us. Okay? What it does tell us is that whatever the two legs are, whole number, fraction, radical 2, radical 3, radical 7, whatever, if you multiply that by the square root of 2, you'll get the hypotenuse length. But then you might have to simplify that hypotenuse length so that it doesn't look like it has a radical 2 in it anymore. Okay? And you might have been thinking the same thing about that 30, 60, 90. If you remember the patterns of 30, 60, 90s, you might have been thinking to yourself, wait a minute, there's no radical 2 in that kind of a triangle, Mr. Hurtillo. And you're right, there isn't in the pattern. The pattern for 30, 60, 90s looks like this. 1 whole number 2 for the hypotenuse and square root of 3 for the longer of the two legs. Okay, the short leg is 1, the longer leg is the square root of 3, which is about 1.7. So it should be longer than 1. There's your 30, 60, 90 pattern. And no, there are no radical 2's in it, but there don't have to be. Okay? The F corresponds to the radical 3. The 7 radical 2 corresponds to the radical 1. So let's write the equation. F over square root of 3 equals 7 radical 2 over 1. To solve this, we're going to multiply both sides by radical 3. Cancels out over there. F is equal to 7 radical 6 over 1. Don't write the over 1. There's your final answer. Okay? So this F turns out to have a radical 6 in its simplified answer. And let's talk about the hypotenuse of this triangle. I want to emphasize my point that the numbers in this particular 30, 60, 90 don't have to look like the numbers in this 30, 60, 90. What this pattern tells us is that the hypotenuse is always twice as long as the short leg. See that? 2 and 1. The pattern doesn't tell us that those sides are whole numbers. It tells us that the hypotenuse is twice as long as the short leg. And so if our short leg is 7 radical 2, what's 2 times that? It would be 14 radical 2. So no whole numbers in this triangle anywhere. No radical 3's in this triangle anywhere. Doesn't have to be. Okay? And there don't have to be radical 6's either. I mean, that just is sort of an accident of the way I constructed these problems. If I had made this side 7 radical 5, then I believe F would have turned out to be 7 radical 15. Okay? Finally, one last problem. This triangle here, I got a 5, I got a 7, I got an H. Is this a 45, 45, 90 right triangle, or is it a 30, 60, 90 right triangle? Well, if you said 45, 45, 90, you're wrong. If you said 30, 60, 90, you're also wrong. I did not mark any of the angles 45 degrees, and I did not mark any of them 30 degrees or 60 degrees. And I did not mark the sides congruent to each other, which would make it a 45, 45, 90. So you cannot use the 45, 45, 90 pattern or the 30, 60, 90 pattern to find H in this triangle. And trust me, on the quiz and on the test in this chapter, some student always does that because they're hurrying. They're just not being careful. Okay? You might have guessed that this was a 30, 60, 90 because it doesn't look like the two legs are the same length as each other. I hope it looks like they're not the same length. So a lot of students then think, oh, that must be a 30, 60, 90. But nope, I didn't put 30 degrees and I didn't put 60 degrees anywhere in this picture. And if you're asking yourself, well, then I guess that can't be determined. Well, that would be wrong also, because we know 2 out of the 3 sides of a right triangle. We can use the Pythagorean theorem, for goodness sakes. 5 squared plus h squared is equal to 7 squared. H is not the hypotenuse. Not in this problem, it isn't. 7 is the hypotenuse, right? So the h goes over here in this equation, not on the right. 25 plus h squared is equal to 49. Subtract 25 from both sides. H squared is 24. And so h is equal to the square root of 24, which is the exact answer, but not the simplified answer, because 24 factors into the square root of 4 times the square root of 6, which is 2 radical 6. That's the value of h, exactly, and simplified. On tonight's homework, I've given you 6 sets of problems in the homework. Set A, B, C, D, E, F, and I think there's even a set G, okay? I want you to do them one set at a time, then check the answers. Check your answers to a whole set of problems before you move on to the next set, all right? Because really, the first 4 sets of problems are very much all the same, okay? Very little different from set to set. If you make 2 or 3 or 4 mistakes in the first set, I want you to identify those mistakes and try to figure out why you're getting to the wrong answers before you do the next set of 6 problems. Otherwise, you are very, very likely to continue repeating those mistakes over and over again. And the more you repeat a mistake, the better you get at making that mistake, right? So you want to find and you want to identify and correct mistakes as soon as possible. So after you've done the first set, check the answers to the first set, okay? Then go on and do the second set. Check your answers to the second set. Then go on to the third, and so on. And I also have some instructions in the homework where by the time you get to a certain set, the instructions may say something like this. If you did the last set perfectly, then skip this set. Or if you did the last 2 sets perfectly, skip the next 2. I forget exactly what the instructions say. But read the instructions before every set, because they might give you permission to skip some of the homework problems. Because really, if you do the first 4 sets of problems perfectly, you don't need to do the 5th and 6th sets because there's nothing new in them. But if you're continuing to make too many mistakes, you should continue practicing, all right? And be on your toes. Some of the triangles are 45, 45, 90s. Some of them are 30, 60, 90s. And I think in the first couple of sets, they're all 45, 45, 90s or 30, 60, 90s. But then watch out, because all of a sudden in one set, some of them are not 45, 45, 90s or 30, 60, 90s, and you have to resort to using the Pythagorean theorem again, okay? So good luck with the problems. Reach out to me or your teacher if you have any questions. And when you come to class next, guess what I'm going to be asking you to do? Right? What am I going to ask you to do in Class Kick if you're my student? I'm going to give you problems just like these, a 30, 60, 90, a 45, 45, 90, and a Pythagorean theorem problem, maybe 4 or 5 of those problems, and see if you can deal with all of them right away. So be prepared for that. We'll see you then.